So hi everyone, thanks for joining me here today. And today I'll be talking to you about Project Panama, Unleashing Native Libraries. So my name is Tobi Ajila. So a little bit about myself. I'm a JVM developer on the OpenJ9 JVM team. I've spent a bit over a decade working on JVMs, mostly focused on the runtime aspect of things. But I've worked on other projects like value types, checkpoint restore, and Project Panama at some point, and as well as others. So a bit about my team. So as I said, it's OpenJ9. OpenJ9 is an independent JVM implementation. So there are others like OpenJDK, Azul, OpenJ9 is another one. It was open sourced in 2017. However, the technology dates back further from the late 90s. Previously was under a different name, but today the open source version is OpenJ9 and the IBM branded name is Semru. So if you've heard of Semru, OpenJ9 is the same thing. All the development is done in open source, so everything is visible. We interact with users in open source and take requests and things like that. So it's a very accessible project. All right, so today we'll talk about Project Panama, and I'll motivate why we need something like this and the kinds of problems that it solves. But before we get started, I'll just do a quick poll to see who knows JNI, Java Native Interface. Okay, good. Keep your hand up if you've used it. Used it? Yeah, okay. And keep your hand up if you liked using it. Okay, that's good. So I'm going to introduce to you a new feature in the JDK that is going to make interoperating with native code a lot simpler and a lot more pleasant. So if you didn't like using it, that's good. That's okay. It gets a lot better. So we'll take a look at the legacy native interop capabilities in the JDK and some of the issues and drawbacks there, and then I'll introduce Project Panama and the main components of Project Panama and how it addresses all of those previous concerns. This presentation is going to be, if you're familiar with C or C++, this is going to be fairly straightforward for you. We'll see a lot of overlaps between the two. But it's not necessary to know C, C++. I'll explain everything as I go. So first of all, what is native interop? Native interoperability. It's essentially the ability to interact with native libraries from Java code. So there's a lot of libraries out there that do a lot of interesting things. And it'd be very nice if Java developers had access to these native libraries. Some common examples are libraries that enable CPU offload. So anything that allows you to offload computation to a different processing environment. CUDA, OpenGL, there's a few others. Machine learning libraries, quite common these days. So TensorFlow, crypto acceleration like OpenSSL. And there's other libraries as well that are very useful. So these are kind of reasons why you would want to interop with native libraries. But the issue is that pre-Panama, doing this was very difficult, and we'll take a look at why. So the ways to interop with native libraries in the JDK previously was JNI. That was the main mechanism, so Java Native Interface. And then, not always, but a lot of times people would use this in conjunction with byte buffers or SunMISC and Safe if you want to interact with the data directly. So JNI is the original native callout mechanism in the JVM. It lets you target a native function and call to it directly. There's even some support for COBOL as well. Now, the issues with JNI is if you're a Java developer, you have to know C or C++, because in order to call the native library, you have to write a native wrapper in C or C++. The wrappers kind of put you in a situation where you have to write a lot of code, because for every native function you want to write, you need to write a wrapper for that function. So if you're dealing with a big library, this is a lot of additional code that you have to maintain. And its only purpose is to just call the native that you are actually interested in. One of the big issues is that native types do not match Java types. Native types have a well-formed layout. The C standard enforces, or not enforces, but kind of describes how types are supposed to be laid out. And compilers have consistency in how they lay out those types. With Java types, if you use different set of command line options, the layout changes. So you can't really overlay a Java object on top of a C type. They don't match. So often you end up using things like longs to represent native types, and you end up losing type information. Another issue is that interacting with native data, native data in native memory, once you allocate it, it lives exactly where it was allocated. But on the heap, things are different, things move around. And so if you want to interact between the two, oftentimes you have to copy things to the Java heap and back and forth. So that's an extra overhead. Some people use sunMISC and safe or direct byte buffers to get around this issue. So you can leave the native data exactly where it is and then just point at it. And the final drawback with JNI is the transitions are slow because you have the extra indirection of having to call a wrapper function before you call the native function you're interested in. So unsafe API, essentially it allows you to interact with pointers from Java code. So sometimes you have to interact with data allocated in native memory. You can just, as long as you know where it is, you can access it using unsafe. The benefits of unsafe is that it's very fast. The JVM optimizes this down to the individual machine instructions. But the drawback is that it's unsafe. It's inherently unsafe because there's no bounce checks. So you can overflow, underflow. It's very easy to crash the VM using this. And if you think about why Java became popular is that it provided safety. It kind of took away those concerns of dealing with raw memory pointers. Direct byte buffers you can think of as a safer unsafe, but it's still limited. So direct byte buffers have a bounce on them, so you won't overflow or underflow, which is good. But you're limited in addressing because it uses the Java int, so you've got 31 bits, given that it's a signed number. The memory management is done by the GC, so it's non-deterministic. So you don't really have much control over how that memory is freed. So I'm going to show you an example here of a native program. This is a C program. So I'm using a library called libcairo, and libcairo is just a two-dimensional graphics library. You can make images and then save it to a file. So what it's doing here is not terribly important. I'm just going to make an image that says hello Devnexus, and then I'm going to write it out to a file. But you can see the code here. It's fairly simple, fairly straightforward. Does exactly what it says, and then you get a picture that looks kind of like that. So if we wanted to do the same thing in Java, prior to Panama, JNI would be the option. So what you would do is you'd have to write a native function for each one of those API points that I was using in the library. And so you can see immediately there's a bit more code because we have to define the native headers. But then in the main function, it's more or less the same. We're just calling the same functions, doing the same thing. As you can see here, we have to represent the structures, the pointers to structures as longs because there's no equivalent in Java. we're using just your regular int literals for some of the macro definitions. I could have defined them, but that's extra work. So it's a little more clunky, but this would be okay if this is all we had to do. But as those who've used JNI before know, there's more work here. So once you've written the Java code, you'd have to run it through Java H tool, which is a Java header file generator, and it generates the header functions for all the native functions that are defined here. And so it looks something like this. I've only put 3 here, but there's a lot more. So this is all generated, which is good. You don't have to handwrite it yourself. But what you do have to write is the implementation of all these functions. So this is handwritten. And so you can imagine if you're dealing with a large library, that's a lot of code you have to write just to pass through a call to a native library. So we can see here, here's the library call we want to call, and we're just passing the arguments all the way through. You can see here, this is where it gets a little tricky because this call here takes a font name, which is a C string. And so we need to convert the Java string into a C string. And so this conversion you have to do manually. And this is kind of, these are some of the issues that you encounter with JNI, is that you've got a Java string that lives on the Java heap. So you can't pass it to the native code. And so you have to copy it off the Java heap here. So that gets string UTF-8 chars there. That's a copy. And then you have to, once you've copied it, then you can pass it to the native function. So there's additional overheads there. And I think the biggest issue is that if all you want to do is interact with a native library, you end up writing a lot of code that you have to manage just to facilitate something that you really want to do. So this is extra overhead that doesn't have to happen. So ideally, the goal is we want something like this, where here's a Java class, it defines a main function, and you'll notice here it's doing something very similar to what we saw in the original example with the C code, except we're just making library calls. So here we've got a API, Cairo_H, which represents our library, and we're just calling functions from that library. This is pure Java code. We haven't done anything fancy here. We're not using magic integer. We have functions that represent the macros. So this is what we would like to have, where you can interact with native code as if you were just calling a standard Java library. So in order to achieve what I previously showed you, there are 5 main things that are required. So first of all, you need an API that allows you to describe native types and structures. So in order to target native libraries, you need to be able to define the types that the native libraries define and interact with them. Secondly, you need to be able to access the data on and off heap to avoid the copying costs. Ideally, you just keep the data where it belongs and not move it around if possible. And that limits your overheads. And third, you need the ability to load the library, load symbols from the library. Currently, you can load libraries, but once you've loaded the library, you can't do anything with it. It helps to be able to do a bit more than just load the library, but actually load symbols. And fourth, you need to be able to call native functions within that library. So you can do this with JNI, but JNI is limited to primitive types. So if you need to pass a struct by value, for example, you'd have to do a lot of copying over in order to do that. And most importantly, we want to make these all these transformations as mechanical, in fact, automatic, such that you can interact with the native library as if you're interacting with just another Java API. So next, we'll look at how Project Panama addresses these. So Project Panama is made up of 3 components. The first is foreign memory access, second is foreign function support, and the third is JExtract. And you'll see that these correspond to to the 5 requirements that I described. So foreign memory access allows you to describe the types and layouts, and also allows you to safely access those things. Foreign function support allows you to load libraries and call the native functions from them. So foreign function support and foreign memory access work together and kind of give you all the capabilities you need. And then JExtract is the tooling on top of those 2 that abstracts all of that away for you. So ultimately, when you're using Panama, you actually don't have to know what's going on under the hood. You can just pretend like you're just calling a Java library. So, the end goal is basically getting to a point where you can't even tell that it's a native library. But in this presentation, I'm going to go over the fundamentals and go over the building blocks so you can see how all of this comes together and how, when you use JExtract, you have an idea of how everything works under the hood. So let's start with foreign memory access. So there are 3 main components here. So there are arenas and memory segments. These kind of control the temporal and spatial bounds. By temporal bounds, I mean the lifetime of memory, and spatial bounds is the range in which that memory is valid. And then there's memory layout. So for those familiar with C structs and unions, this will be very similar. And then memory access handles. So this is the mechanism that allows you to access the data. So a memory segment is an abstraction that describes a contiguous memory region. And this memory region can be on or off heap. It enforces the temporal and spatial bounds. So temporal and spatial bounds exist in languages like C and C++. When you allocate memory with malloc, that memory is created, it's valid, and then when you free it, it's no longer valid. So there are temporal bounds with that memory. It's just that they're not enforced. So if you try to reference the memory after it's freed, you have undefined behavior. Likewise, if you allocate 100 bytes and you go beyond the 100 bytes, you've kind of gone beyond the spatial bounds, but C doesn't stop you from doing this, but the behavior is undefined. So with memory segments, there is enforcement of temporal and spatial bounds. If you try to go beyond the constraints, you get an exception telling you you've done something wrong. And so the behavior is well-defined. You kind of avoid these potential security concerns when you go beyond the bounds. So there's enforcement of spatial and temporal bounds, and there is also enforcement of alignment constraints. And alignment constraints, they're relevant on, some architectures care more about this than others, but some architectures, the way you interact with the memory has to be done on certain memory ranges. So, for example, if you're going to load a 4-byte piece of memory, you have to do it on every multiple of 4 bytes, so 0, 4, 8, and so on and so forth. An arena is a memory segment provider. So it's what sets the scope for the memory segment, what determines which threads have access to the memory segment, sets the alignment constraints. So the arena essentially determines the constraints on the memory segment. The arena is kind of like the owner that supplies the memory, the resources to the segment and sets the rules. And then the memory segment is the facilitator that enforces all the rules. So there are 4 main arenas: global, auto, confined, and shared. But you can define your own as well, so you're not limited to these. And these 4 arenas are differentiated by 3 properties. So bounded lifetime. This essentially describes the life cycle of the memory associated with the arena. So with global arena, there is no bounded lifetime. And what this means is that any memory returned from this arena is alive forever. It doesn't ever die. And this is this can be useful in cases where you want to represent memory that is returned from something external to the JVM. So you have no idea when that memory is invalid. So with global arena, now you have a way to abstract that kind of state. The other property is explicitly closable. So this describes if the memory returned here is explicitly closed, as in explicitly freed. So in the case of auto, so in the case of global, it is not explicitly closable because it's never closed. In the case of auto, it's not explicitly closable because that is controlled by the GC. So the programmer is not going to determine the life cycle of the memory segment. The GC will determine when this is when the memory segment is dead. And this is done by just tracking references. But in the case of confined and shared, this is done explicitly. And we'll see later in examples that even though it's explicit, if you use the try with resources programming model, it's kind of done implicitly. So it's not like malloc free where you have to insert those things. It's actually a lot simpler than that. And then the final one is multi-thread access. And so what this means essentially is it determines which threads have access to the memory in that arena. So in all the cases except for confined, any thread can access it. In the case of confined, only the thread that created the arena can access it. So here is an example. So at the top, we have global arena, which you can just get from the arena API. And we're allocating 100 bytes with the alignment constraint of 1 byte. And so we return memory segments. And below that, you can do the equivalent with the other types of arenas. So here is another example. In this case, we have a confined arena. And as I said, if you are creating a confined arena, the scope is explicitly closable, but there's no code here that's closing anything, and that's because with try with resources, if you look at how the JavaC compiles these lines of code, you'll see that there's going to be a call to close scope, which closes the scope once you've exited that try with resources block. So everything is done for you implicitly, so long as you use the structure. So scope, I've mentioned a few times. Scope is an actual type that is part of an arena, and then it's applied to the memory segment when it's created. It essentially controls and enforces that memory is only accessed while the scope is still live. So, and it behaves very similar to the scope conceptually in C++. So for the most part, this is not something you actually have to interact with. There are APIs that allow you to acquire the scope from the arena. So here's an example where we can get the scope and then query if it's alive. In this case, it's going to return true because we're within the confines there. In most cases, you never have to deal with it, as long as you use the try with resources with explicitly closable arenas. It's just handled implicitly. Okay, so back to memory segment. So this is an abstraction that describes a contiguous memory region. So here are the internals of a memory segment. So it has a field that indicates the size of the memory segment, and then a Boolean to indicate if it's read-only or not, and then a scope that determines the life cycle of the memory, as well as thread ownership. Now, there's multiple types of memory segments. So a memory segment can point to memory on heap or off heap. So if we're pointing to off heap memory, in this case, we're dealing with a native memory segment. And so it's going to have a field in addition that is essentially a pointer. So it points to the address of the native memory. If we're dealing with an on-heap memory segment, that is a heap memory segment, it's going to have two fields. And the reason, as I explained earlier, is that when you're dealing with things on the heap, let's say, for example, those objects on there those shapes are Java objects. Those objects, when the GC is doing memory reclamation, most GCs, modern GCs that is, will move objects around. So unlike native memory, where you know exactly where it is all the time, on the Java heap, you have no certainty of where an object is. So the way you interact with things on the heap is via a managed reference. And so the GC manages these references. When it moves things, it updates the references. And so in Java, the only way to kind of represent a managed reference is with an object. And so that's why when we're dealing with things on the heap, we always have an object. So the object essentially is your base. It's where it points to where the memory is. And then the long offset there is within that, from that base, what do we want to refer to? So yeah, that's just an example of things moving around. There is another type of memory segment, native mapped memory segment, but it's useful to in cases where you have file-backed memory. But I'm not going to go over that just for brevity. So here's an example of how you can interact with memory segments. So the top example here, it's just creating an off-heap memory segment, similar to what we saw earlier. In the second example, we're creating an on-heap memory segment. And you'll notice that we're not using an arena here. That's because on-heap memory segments are implicitly from the auto arena because they're managed by the GC. And then in the third case here, we're making a segment read-only. So it's an operation that changes the constraints of a segment and returns a new one. So anyone who's dealt with native memory allocation with malloc knows that if you use it very frequently, it can be slow. And that's because of all the memory management bookkeeping that occurs when you call malloc. Also, in multi-threaded environments, there's also synchronization concerns that you have to factor in as well, which can increase the overhead. This is a common problem. Most GCs in the JVM will use thread local allocation buffers. And essentially, this is a practice where you acquire a large chunk of memory and assign it to a thread, and then you sub-allocate out of that thread so that there's no contention when you're allocating memory. So with memory segments, you can do something similar. You can allocate a large segment and then sub-allocate from that segment. And so the overheads, if you need to do frequent memory allocation, this reduces the overheads. So I have a little example here where we allocate a pizza. I knew this talk would be right before lunch, so I wanted to get your appetite going. So we have a pizza here, and then we can sub-allocate a slice out of it. So the first parameter is the start. The second parameter is the size. So we're only sub-allocating a byte, and then the second slice is another byte from the second offset. So yeah, so that concludes memory segments. We'll take a look at memory layouts now. So the memory segments and arenas allow us to allocate memory and put some rules around them. But memory layouts allow us to describe what the memory looks like. So if you're familiar with the type-def operator in C or C++, memory layouts is essentially, it essentially describes things that you can apply the type-def operator to. So here's the type hierarchy of memory layouts. There are four main types of layouts. Value layouts. So these represent primitive types. So types are not composed of anything else. And then there are group layouts. These are a composition of types. And then there's sequence layouts. These are repeating types. And then padding layouts. These are a bit of a special case. Oftentimes, compilers will insert bytes into structures to ensure that the alignment constraints of the underlying architecture are met. And so the gaps are called padding bytes. I'm not really going to talk about it here, but because we're interacting with native memory here, we need a way to represent all the memory. So that's why this exists. So value layouts, you'll see that the 8 Java primitives are represented here. So Boolean, byte, all the way to long and double. And then there's an extra one here for address. So this represents the address size on the particular platform. These are the building blocks for basically all the other layout types. So here's an example of how to use these. So with a given segment, you can request the layout of an int, for example. And so what this means is you're going to index this segment using an int stride. So in this case, we're just getting the first index and representing it as an int. And you can see here that once you get it, you're getting a Java primitive int. So you're dealing with the primitive type. And you can do the same thing with float. When you're dealing with addresses, though, because we don't really know what that memory is, it's still using the memory segment abstraction. And you can do something similar with var handles, which I'll go over a bit more in detail later. But you can create a var handle from a layout type, and this allows you to access the memory as well. Okay, so the second is group layouts. So these are composition of memory layouts. There are 2 kinds of group layouts. So there are struct layouts, which you can think of as the equivalent of a C-struct, and then there are union layouts, same thing. So here's an example. So we have a struct definition on the left. We're define a point 2D with 2 fields, X and Y. And if you look on the right, you can see the equivalent definition using Panama APIs. So it's very similar. And then at the bottom, we have a line composed of 2 points. And you can see the equivalent definition on the right with the Panama APIs. So it's very, very similar. There are also union layouts. So unions, and in this case, it has the same definition as unions in C, where the union is a compound type where it takes the shape of the largest member, and it can represent any member, but only one at a time. And so the same thing with the union layouts, with memory layouts, behaves in the exact same way. And you can see, like with the group layouts, they can build on each other, just like you can build on the definition of other types with structs and unions in C. And then there's sequence layout. So sequence layout you can think of as arrays. So we've got an example here where we have 100 points. And with Panama, you would just do a sequence layout, supply the number of repeating layouts, and then the layout type. Right, and so finally, there's a zero-length memory segment. I actually showed you this earlier in an example, but if you recall the example where we were loading an address from a segment. So a zero-length memory segment is a special case memory segment where you want to model a region where either the length of the region is unknown or the lifetime is unknown. So a common example is if you're dealing with a native API that returns a char pointer or const char pointer for a string. You know where the string starts, you don't know how long it is. So in this case, you can't associate a size with it because it's unknown. You kind of have to read the string until you get to a null terminator before you know the size. So Panama allows you to represent these things with zero-length memory segments. And the way you interact with it is that you do the reinterpret operation and put a bounds on it, and that lets you then access the memory. So in this example, we have a segment from native, and we want to get it with an address. So when you do this, the size is 0. But then when you reinterpret, what you're saying is, we're going to put a bounds on it for the first 4 bytes. You can do something similar as well, where you do this within an arena. So when you get the segment, it's unbounded initially. And when you reinterpret it, you can bind it to an arena. And the last parameter here is it takes a callback that allows you to run some code once you exit the confines of the arena. And lastly, we'll look at memory access handles. So we saw how to allocate the memory, how to describe the memory. And in this section, we'll look at how to interact with the memory. So memory access handles are essentially references to two variables. It's based on var handles, which was released in Java 9, but these are references to variables that allow you to access a static, non-static array on heap, off heap variables, and perform a variety of access instructions on them. So we looked at example earlier, but we'll look at this in a bit more detail. So in this example here, you can see the C code. We're getting points from the 37th element of a point array, and then we're getting the X field from that point. So the way to do this is first we have to, with Panama, you first have to describe the path to that variable, and that's done with the path elements. So when you use the var handle API, you can supply path elements that describe how to get to that variable. And the variable must always be a value layout. So you must always be referring to something that is a primitive or an address. And then once you do that, then you can create a var handle, and you can perform a variety of operations on it. The last field here is the offset. Typically, this will be 0. Now, there are cases when dealing with native APIs where some cases you want to write a struct by value. So you're not dealing with the pointers here, you're dealing with the actual struct. And in C, when you are assigning structs, internally what's happening is that you're copying a region of memory. With Panama, you can't do that with this approach. Instead, you have to do an explicit copy. So in C, it's kind of done. It looks like a normal assignment operation, but it's really doing a copy. In Panama, you explicitly copy, and that's just so that you know exactly what's going on. With var handles, there are a variety of access modes. So for those familiar with C++ atomic library, this is very similar. You can do things like get and add, compare and exchange. There are weak and strong operators as well. So it's very similar. In fact, anything you can do with unsafe, you can do with var handles. But the key difference is that with var handles, there's additional safety in that the bounds are enforced and the scope is enforced. So you can only access memory that's live within the spatial bounds that have been set. So it's less likely that you're to crash the VM using this. All right, so we've looked at how to interact with memory and describe memory. Now we'll look at the foreign function support. So in this section, we'll see how one can load libraries and call native functions in the library, which is really the main goal. So there are 6 main components here. First is symbol lookup, so how to load the libraries, how to find symbols. Second is linker, so how to link to native functions. Third is downcall, so how to call the native functions. And then opcalls is kind of like a special case where you're dealing with function pointers. So some native calls will take parameters that are function pointers, which are essentially pointers to other functions that can then be called. And then we've got variedit calls where the parameters are variable, and then linker options. So so symbol lookup is essentially a mechanism to load libraries and look up symbols within those libraries, or even global variables like erno, things like that. So it behaves similar to system load library. So in this example, we're using library lookup to load libdemo within the confines of an arena. When you use system load library, it's loaded by the class loader. So the library remains loaded so long as the class loader is loaded. As soon as the class loader is unloaded, then the JVM can unload that library. In this case, the library is loaded and remains loaded for the confines of this scope. And then once we've loaded the library, we can search for symbols within the library using the find or throw API. So it actually behaves a bit more like DLOpen or DLSym, if you're familiar with those APIs. The library lookup functions like DLOpen, and the find is like DLSym. So there are three main library loading mechanisms. So there's library lookup that we just looked at, which loads the library. There's loader lookup, where you can query symbols in libraries that the class loader has already loaded. So if you had some other JNI code that called system load, for example, and loaded some libraries in the class loader, you could use the loader lookup to search for symbols in those libraries. And then there's default lookup that essentially provides a lookup for symbols that are in the system library, so things linked with standard C. So here's an example. So we can use the loader lookup to look for a symbol if we'd loaded the library previously. And then with a default lookup, we can look up for things in the system library, so like strlen or printf or malloc, etc. So linker support. So the linker API allows Java code to link with native functions. And then it allows you to create a down call linkage, which is a native call out, so Java to native, and then up call linkage, which is native to Java, which can then be wrapped in a memory segment and passed as a function pointer. So those are the main usages of the linker API. But it also lets you create memory layouts that represent the native types as well. So in the previous section, we looked at the value layouts, and there were 8 Java types and then address. But when you're dealing with native types, they don't always map one-to-one with Java types. Depending on what platform you're on, the size of an int can either be 32 bits or it can be 64 bits. So the linker API also allows you to create the native layout of a type. So you can give it the type you're interested in this case, long, and then it gives you the value layout that represents that type. So the translation from native sizing to Java sizing is done automatically for you in this case. So down calls. So down call is the main mechanism to call native functions. It requires something called a function descriptor, which basically describes the signature of the native function that you want to call, so the arguments and parameters. And this is done using memory layouts. And then linker options, these are optional. And then the function address. So, and you'd get access to the function address by doing a lookup of the symbol. So we'll look at an example here. So we have a native function called createPoint that takes 2 parameters, x and y. So defining a linkage to this is shown at the bottom. So first of all, we search for the symbol, and then we create the native type equivalents. And then we create the function descriptor, so you can see it returns a point 2D, and the two parameters are two ints. And then we create a down call handle to that function using the function address and the function descriptor. So down call handle is a type of method handle. Method handles were introduced, I believe, in either Java 7 or Java 8. And these are essentially references to methods. So var handles are references to variables, method handles are references to methods. And they're similar to reflection, like Java reflect method, but these are much more lower level abstractions. So with a method handle, you can invoke it. And so in this case, we've got a method handle that's a native linkage. So you can see the equivalent up there where we are calling the create points. The Panama equivalent will just be an invoke exact with the parameters. So like I said, there is a special case where you're dealing with a native function that takes in a function pointer. So the canonical example is qsort, where you've got your array or a repeating type that you want to sort. And then the last parameter there is your compare function that does the comparisons. So like I said, the goal of Panama is that you're able to interact with native libraries purely from Java code, as if you were just writing Java code. So typically what you would do in this case, if you're using a native function, is you define your compare function in native code and then pass a reference to it. But with Panama, you can do this entirely in Java code, and I'll show you with an example. So the same thing, we'll define a function descriptor for the call. And so all the pointers are represented as addresses, and then we've got the size t for the size fields. And then we define a function descriptor for the function pointer that's going to be passed to qsort. And then we're going to create a method handle that points to a Java function that does a comparison. And so in this case, I haven't shown the code for this, but I have a qsort class that has a function called compare, and I'm going to create a method handle to that method. And then in an arena, I'm going to allocate an upcall stub. And upcall stub is essentially, it provides a mechanism for native code to call into Java and then wraps it into a memory segment. So you've got, you essentially have something similar to a thunk where it has the native linkage for the platform, and it can be called, it can be invoked just like any other native method, except the thunk is going to call into the JVM and execute Java code and then return. So that's what's going on there with the upcall stub. And then I'm going to allocate the array using the arena and then call the function using my compare function. And so you can see in this case, no native code was written, everything's done in Java. And then here's an example with printf, with the variadic arguments. So with linker options, you can define where the variadic arguments start, and then the down call linkage takes care of the rest. So here's an example. If you want to do printf, hello Devnexus. This is how you do it with Panama. And you can see with strings, I'm using arena allocate from, which means that it's allocated in native code. So in the earlier JNI examples, we would allocate it on the heap and then do the copy to native. In this case, we can allocate directly into native code, and so we avoid the overhead of copying from on heap to off heap. And then we can perform the call. So this kind of concludes the foreign memory access and foreign function support. And earlier in the talk, I promised that this would be simpler, and in a lot of these cases, you can see that's actually more code than the native equivalent. And that's where JExtract comes in. A lot of these operations they have to do are quite mechanical. If you know the native type you're dealing with, it's just a pattern that you follow. So because it's quite mechanical, it's very easy to automate. And that's what JExtract does. So it generates these bindings for these functions for you so that you don't have to deal with all the mechanics of making memory layouts and down calls, etc. It generates everything. So JExtract is a Java binding generator. It has a dependency on Clang. That's how it parses the header files to get all the native structure information. It's a separate component. It's not part of the JDK. It's a tool that's produced. It is produced by OpenJDK. It's still in early access phase, but you can use it, you can download it, and make use of it. So it's a tool that parses header files and generates Java methods to interact with the native libraries. It also generates static initializers to do the library loading. So earlier we looked at how to load libraries and load symbols. All of that is taken care of under the hood. All the memory layouts for the structures, etc., the down calls for native functions. So using it's fairly simple. So I downloaded JExtract 22, which I believe of this week is still the latest version. So what you would do is you tell it where to look for all the header files, and then the output tells it where to put all the Java files that it generates. And then you can define a package that you want all the generated bindings to be under. And then the library name, and then the actual header file. So that includes, similar to if you're compiling a file, you include there as kind of like your -I. And then the library command at the bottom is the actual header that you want to generate the bindings for. So I will show you an example of what this looks like. Okay, so I ran this earlier, and I put everything here in libcairo. And what you'll see is, actually it might be easier to just look at it here. But if we look at these functions here, we can see that we have a down call handle for each function. And if we look at where it's defined, you can see here that it's doing a lookup. Just like we saw in the example, it's doing a lookup for the function. The address it gets by looking at the library for the symbol. The descriptor it generates, you can see that it's generated the function descriptor here. So for every function defined that it found in the header file, it generated the down call for it. And for every struct that it found in the header file, it also generated a file here that represents that structure. So you can see there's a lot of files here. It's a fairly sizable library, but everything is automatically generated for you, so you don't have to hand write everything yourself. And so the result is that when you want to use it, you're essentially using it like you are using any other Java library. So if I go here, I can hear all the native types that were represented here, and hear all the macros. So I can use things by name instead of using magic constants, and hear all the functions, etc. So with JExtract, essentially we get to the point where you can now start to treat this like it's any other Java library. Some of the elements that I talked about earlier, like arenas, is still relevant. So over here, I'm allocating a string. So I'm allocating it from the arena. So that's quite relevant. The loading the library, this was done within the static initializer of the API. So it's not confined. It's not bound to an arena in this scope. But I believe there is a way to do so, to explicitly load it and bind it. And of course, so it generates source files. So if you want to change anything, you can just go in there and change it yourself. But the automatic generation is probably good enough for most use cases and does greatly simplify using native libraries. Yeah.
What's the performance compared to JNI?
Yeah. So for down calls, calling out to a native, it's quite comparable, so long as you're dealing with simple arguments. So we're talking things that are primitives. If you start, primitives are pointers. If you start using structs by value, then it's a lot more complex, and the linkage itself is more complex, and you start to see the overheads get a bit larger than what you would, than a comparable JNI call. And in some ways, it's an unfair comparison because you can't do by value, composite types by value with JNI. But for the most part, as long as you stick to the simple primitives and pointers, the performance is quite comparable. There is, so in most JVMs today, I know OpenJ9 does this, but for certain, in certain cases, so when doing JNI, there's always a handshake the thread has to do that basically notifies the VM that I'm going off the JVM. And this is important for cases where the GC wants to halt all the threads. If you're in native code, the GC has to know that you're in native code so that it knows that I can ignore you and block you from returning to Java before interacting with the heap. There's some optimizations in the JVM that basically allow a thread to call out to native code while still behaving as though it was in Java code. And the reason for this is to avoid the handshaking, the thread handshaking when going out to native and coming back in. Panama does provide an option, a linker option that says is trivial. And what this means is that when calling this function, I'm not going to do any handshaking. And so the calling sequence is very fast. Now, it's a very powerful mechanism because if it's misused, what it means is that you can essentially block a GC from happening. So it's something, in the JVM, we do this for natives that we know about. We know that these are non-blocking natives. They're just calling out, calling back in, not blocking on anything, so it's safe. But if a user wants to do this, they have to be very careful to not do any blocking operation. So with the linker options, you can get the same performance as JNI. Yeah. Any questions on that? Yeah.
Your examples show plain C and structs and things like that.
Yeah.
If you're talking to C++ and you've got classes with inheritance and all of that,
yeah,
how do you communicate with those?
Yeah, so I forgot to mention earlier on. While I did say C, C++, what I really mean is C++ with externcy. So it's really a C API. You can use APIs defined by C++, so long as you make sure they're exposed with C linkage. In theory, you could create a binding mechanism that supports C++ because you've got all the tools to do that. You just need to know, the rules with name angling. You need to know the rules with how the compiler is laying things out. So everything is possible to do. It's more complicated. And to my knowledge, JExtract does not support it yet, although there is discussion that it might be supported in the future release. Yeah.
How hard is it to work with Kotlin to talk to C through Project Panama?
Yeah, so to be honest, I'm not very familiar with Kotlin, but as far as I know, you're going to have to do the usual tricks that Kotlin has to do to interact with Java APIs. You'll have to do it. There's no, to my knowledge, there's no built-in support in Kotlin to take advantage of Panama. Yeah.
And so like the JExtract tool is not going to be an option, I gather, because it's going to generate Java code.
Yeah, exactly. Yeah. Now, there's nothing stopping someone from writing a Kotlin version of JExtract. Yeah.
You didn't mention JNA, which has been everybody's escape from JNI. Do you have any comments about where this fits relative to JNA? I know you can't do callbacks like you're up.
Yeah. Yeah, so I looked at JNA a while ago. JNR was another one. You might know better than me. Is it still an active project?
Well, I don't.
Oh, okay. Yeah, so I know it was used a while ago because for similar reasons that Panama has been created. It was, I know the JRuby guys needed something to generate because they were calling out a lot and they wanted just something to kind of automate that sequence. It solves kind of the same problem in a different way. It still has to use JNI. JNR, I think they created their own native sequence, but I believe JNA I believe that still used JNI. And so it's, I would say, I would describe those as kind of like legacy workarounds for JNI. Panama is certainly a supported way of achieving the same things as part of the JDK, so you know it'll be there forever. And it will continue to be optimized. And so it's, I would say that's the way forward.
And just be sure all platforms are covered.
Yes. Yeah. All right, so yeah, so we kind of looked at the end goal here. I'll very quickly go through the rest. So just a little history of this project. It started in the mid-10s when in JDK 14, I went through a series of incubator preview stages. But as of JDK 22, which was released last year in March, this feature is effectively GA. So if you're on 21, most people are either on 17 or 21. So if you're on 17, you can access it with the incubator flags. The 17 APIs are different. So the examples I showed you are based on the JDK 22 changes. So if you're using JDK 17, more or less you can do the same things, but the APIs are different. JDK 21 and JDK 22, the APIs are the same. So if you're on JDK 21, all the examples I showed you, you can run. You do have to enable preview in order to use it though. But 22 and onwards, it's there, it's a standard feature. The next LTS release is JDK 25 coming out later this year in September. So for most people, I think that's when there'll be the first real chance to use this in production. JExtract is still in EA. The latest EA is JDK 22. I don't have any predictions as to when it'll go out of EA, but that's something that's still under active development. So yeah, this concludes my talk today. So I think we're out of time, but I'll be at the booth. There's an IBM booth a little down the hall. So if you want to discuss more or talk about OpenJ9 or JVM topics in general, happy to talk with you. And it's just a link to some other resources and online talks that we do. But thank you for joining me. I hope you've enjoyed this talk.